Large language models are capable reasoners, but they operate inside a vacuum. Their knowledge is frozen at the moment their training ends, and they cannot natively read a local file, query a live database, or interact with the outside world. To bridge that gap, developers currently build custom integration code for every software tool an AI needs to use. Connecting an agent to a calendar requires one specific API bridge. Connecting it to a document store requires another entirely. This scaling problem is a matter of simple math. If a team uses 5 different AI agents and wants them to interact with 10 software tools, they have to build and maintain 50 separate integrations. This results in a fragile architecture. If just one software tool updates its API, the connections to every AI agent break simultaneously, requiring a constant cycle of manual repairs. The Model Context Protocol, or MCP, is an open-source standard designed to bypass this bottleneck. It acts as a universal translation layer between AI models and external data. By standardizing the communication rules, 5 agents and 10 tools only require 15 total connections to a central hump. If a developer builds a single MCP server for their tool, every compatible AI agent can immediately discover and use it. Standardizing how models request context is the only way to ensure the AI ecosystem can scale without collapsing under the weight of its own maintenance. Every MCP interaction relies on 3 core entities: the host application, where the user works, the client, translating requests, and the server, holding data. When these components connect, they initiate a capability negotiation. The client interrogates the server to find what data and tools are available, allowing the AI to dynamically map out its environment. The server exposes these capabilities through 3 primitives. The first is resources, read-only data, like text files or API responses, that provide the context the AI needs to know before it formulates an answer. For example, an SQLite MCP server can expose an entire company database as a resource. Instead of relying on a guess, the AI pulls live, authoritative records, like employee IDs or sales figures, straight into its working memory. This illustrates the difference between traditional RAG and an MCP query. While RAG relies on semantic approximations of document chunks, MCP extracts the exact, intact row from a relational database. This avoids the inaccuracies of vector search with structured data. By fetching facts exactly as they exist on the server, the resource primitive turns a static language model into a real-time information engine. The second primitive is tools. While resources dictate what the AI knows, tools dictate what the AI can do. These are executable functions that allow the model to manipulate external systems. If a user connects a file system MCP server, the AI agent dynamically discovers that it has permission to read, write, and traverse the folders on that specific computer. This enables complex automated workflows. An AI can locate a bug, write a fix for it, and push to a repository. To make that happen, the AI client sends a standardized request specifying the tool and arguments, transmitting it to the server. The server executes the action and sends a confirmation payload back, ensuring the AI knows the task was successful. The third primitive is prompts. These are reusable templates that guide how the AI behaves during a specific task. Developers use these templates to ensure the model follows specialized rules. Instead of relying on manual instructions, the server provides a pre-written prompt that forces the AI to adhere to enterprise workflows. By combining read-only resources, executable tools, and guided prompts, MCP grants an isolated language model agency over a complete digital workspace. MCP wraps existing REST APIs into a format navigable by language models. The difference is in the audience. Traditional APIs are built for deterministic execution by human developers, whereas MCP is built for dynamic discovery by autonomous AI. Granting an AI dynamic execution power also introduces serious security risks. Connecting an agent to external servers creates a complex attack surface. One specific threat is unauthenticated sampling. A compromised MCP server can silently inject hidden prompts directly into the AI client's processing stream, bypassing the user interface to hijack the agent's logic. The current defense against this is mandatory human-in-the-loop authorization. Before the AI can execute a critical action, like deleting a file or modifying a database, the host application requires the user to manually approve the request. Researchers are also developing protocol extensions like Attest MCP. This uses mathematical capability attestation to verify a server's identity before granting it privileges, stopping malicious payloads before they can propagate. Despite these hurdles, standardizing the connection between models and systems moves the industry from passive conversational bots to active, universally connected digital workers.